In this video we are going to look at the method of stationary phase. So this method is to study the asymptotic behavior of integrals of the following form. So integral from a to b of f of t e to the I lambda phi of t dt. So again, this is in the limit as lambda becomes bigger and bigger and bigger. So the functions f phi and the constants a and b are all real. Okay, so where f and phi are real, well behaved functions. Okay, so here we are going to recall that e to the I theta is cosine theta plus I sine theta. So this is one of Euler's formulas. What it means is that this integral here is just an integral of sines and cosines. So this we can rewrite as integral from a to b of f of t cosine lambda phi plus I times the integral of similar expression but with sine this time dt. Right, so once we put it in this form, then it makes it easy for us to see that these functions or this function is going to be oscillatory in nature. It's going to oscillate because it's a function of sines and cosines, and as lambda becomes bigger and bigger, because as you can see, lambda here is like your frequency. So as lambda becomes bigger and bigger, the function is going to oscillate rapidly. So for large values of lambda, the function or the integrand oscillates rapidly in the interval a to b. So when it oscillates rapidly, then the integrals or the areas under curve are going to cancel out, because some of the areas are going to be positive and some of the areas are going to be negative, because I've got your function like this, and then it's oscillating. So some of the areas are going to be positive and some of the areas are going to be negative. But what we're going to note is that the rapid oscillations are going to be absent from the vicinity of points where phi have got stationary point. So these oscillations are going to be rapid wherever phi is also changing rapidly, but in the interval of regions where phi is not changing rapidly, then the oscillations are not going to be rapid as well. So let's say here, except in the region where phi of t is varying slowly. Except where this function is varying slowly, and this is going to happen in the vicinity of the stationary points of phi. Stationary point, let's just assume there is one for now, of phi. Okay, so this vicinity is going to be called the points of stationary phase. So these are called points of stationary phase. So called points of stationary phase. So this is where the method gets its name. Like I've already said, away from this region, the contributions to the integral will cancel out because they will have opposite signs. So let's actually have a look at this experiment graphically. So imagine we have we're just going to look at the interval between -2 and 2. So right now we have got the graph of x, and x is a function that does not have a stationary point. So let's see what happens if we make plots of cosine lambda x. So when lambda is 1, there you go, cosine is going to look like that. Now suppose we start increasing lambda, say to 10, and then you can see that we've got these rapid oscillations here, and the areas are going to cancel out almost basically exactly. For 20 again, so if you integrate from -2 to 2, these areas are going to cancel out. Now let's look at a function now with a stationary point. So suppose we have got x squared. So there is the graph of x squared. So let's look at the graph of cosine of x squared. So graph of cosine of x squared is going to, alright, so that's your graph of cosine x squared. Now let's suppose I multiply it by some lambda, and let's take lambda to be 10. Now again, you can see that this graph is oscillating rapidly away from the stationary point, but around the stationary point you can see that there is going to be a region where the areas are not cancelling out. So this area this side and this area this side are not going to be cancelling out. Let's see what happens as we keep increasing, say, our lambda. If this is cosine 20 x squared, still we maintain around the stationary point there is an area that is not cancelling out. Let's just do 50 x squared lastly, and then again you can see that the areas away from the stationary point are indeed cancelling out, but in the vicinity of t equals to 0 or x equals to 0 in this case, this graph has got areas that are not cancelling out. So this is the basic idea of the method of the stationary phase, that the major contribution of this integral is going to come from the neighborhood of the stationary point of the function phi. So, and these points are called the points of stationary phase. Okay, now before we continue with the method, there is a very important integral that we have to derive, that we are going to use in working out the method of stationary phase. So we are going to derive the result. So this result says integral from minus infinity to infinity of e to the I lambda x squared dx is equal to pi over lambda to the power half, that's your square root, I pi over 4. So we're just going to derive this result here. There is a corresponding result with a negative in your exponent here. So if that's negative I lambda x squared, then that is going to be negative I pi over 4. I'm going to leave that one to you as an exercise to derive. So we need to derive or prove this. So first we are going to express this. Let's say proof. So we're going to note that since this integral is even, then we can write this as 2 times the integral from 0 to infinity of e to the I lambda x squared dx. And then we are going to set u to be equal to lambda x squared, which means that x is going to be actually u, sorry, this is u squared here. So x is going to be u over square root lambda, and hence dx is going to be du over square root lambda. So we can rewrite this. So we're going to have integral from minus infinity to infinity of I x squared dx is equals to, it's going to be 2 over square root lambda integral from 0 to infinity e to the iu squared. Right, so this is now the integral we are going to work with. We are going to appeal to complex analysis to work this integral out. So we're going to consider the complex integral. So we're going to consider the integral of iz squared e to the iz squared dz, where c is going to be a contour that we show below. So where c is shown below. So basically C is going to be a sector shaped contour. One of the sides is going to go through the line y is equal to x. So that is the 45-degree line, and that's a sector. So this is going to be our contour C, and of course this is going to be traversed in the counterclockwise direction. If this is R here, then along this horizontal side of the contour, we are going to have z is equal to x. And then along this side, we're going to have z is equal to re to the I theta, and along this side we're going to have z equal to ie to the I pi on 4. This angle here is pi on 4. Okay, so we're going to call this one C3, we are going to call this one C2, we're going to call this one C1. Now by Cauchy's theorem, since this function is analytic, then an integral of this along this contour C is going to be 0. So integral along C1 plus integral along C2 plus integral along C3 of e to the iz squared is going to be 0. This is by Cauchy's theorem. All right, so the thing to do, or the trick with these, is that with functions that are analytic everywhere, then you can start with any closed contour, and then you can deform it, because the integral along any closed contour should be equal. So right now we're going to start with this closed contour, and then we're going to deform it by letting r go to infinity. Now, so let's start with C3. So along C3, z is equals to e to the I re to the I pi over 4. Z squared is going to be r squared e to the I pi over 2. So this is going to be the same as IR squared. And then dz is going to be equal to e to the I pi over 4 times dr. All right. And then the variable is going to be r there, and r is varying from big R to 0. So our integral is going to be, so along C3, e to the I z squared dz is going to be the integral from r to 0. E to the I z squared is ir squared, and then dz is e to the I pi over 4 dr. So what's going to happen is the e to the I pi on 4 is a constant, and then we are going to flip the integration limits, and so in k a negative, and this is going to be e to the minus r squared dr, because I times I is -1. Now so in the limit as big R approach infinity, okay, this integral is going to be equal to negative e to the I pi over 4 integral from 0 to infinity e to the minus r squared dr. But this is a standard integral, gamma function integral, the value of which we know. So this thing is going to be negative e to the minus I. No, actually the negative is just there, not in the power. I pi over 4, and this is going to be square root pi over 2. So that is a standard gamma function integral. Now let's look along C2. So along C2 we got z equal to big R e to the I theta, where big R is a constant. So dz is going to be IR e to the I theta d theta, because the variable there is theta, and so z squared is going to be r squared e to the 2I theta. So this is going to be I squared into cosine 2 theta plus I sine 2 theta. So the integral, so along C2 e to the iz squared, so this is going to be equal to, now along this contour, theta is varying from 0 here to pi on 4 there. So our integration limits are going to be 0 to pi on 4. Then we're going to have e to the I z squared is r squared cosine 2 theta plus I sine 2 theta. Then dz is I r e to the I theta d theta. Okay, now so at this point what we're going to do is we're going to take the magnitude of this integral. So the magnitude of e to the iz squared integral of e to the iz squared is going to be the magnitude of these terms inside. So actually we are going to have so this is going to be equivalent to, or is going to behave like, the integral from 0 to power on 4. The magnitude of I is 1. The magnitude of e to the I something, where that something is real, is 1. The magnitude of r is just r. So, and then here the magnitude of e to the ir squared, this term, is going to be 1, but I times I here works out to -1, so that's going to be the only term that is going to remain from that e term, and then we're going to have r d theta there. Now this integral, we can find an upper bound easily by considering the following two curves in the interval 0 to pi on 4. So first, the function y equal to sine 2 theta is going to have a maximum when theta is pi on 4. And then if we look at the straight line joining that maximum and the origin, then the straight line equation of that is going to be 4 theta over pi. Now notice that this curve is always bigger than the straight line. Since 4 theta over pi is always less than sine 2 theta in the interval between theta ranging between 0 and pi on 4, which is the interval of our integration here, it means that if we replace this function by this function here, okay, the resultant integral must be bigger because of that negative there. Okay, so what we're going to do is we are going to say the integral from 0 to pi on 4 of r e to the minus r squared sine 2 theta d theta. Okay, so that one is always going to be less than or equal to the integral from 0 to pi on 4 of r e to the minus r squared times 4 theta over pi. So we're saying since this one is smaller, since this is smaller than this one, then this integral is going to be bigger because we're not dividing by, because this is negative, we're dividing by a smaller value. Okay, and then of course, so we're saying basically this function is bigger than this one. But this function we can integrate without a problem. So we do that. So its integral is going to be minus r, and be pi over r squared e to the minus r squared for theta over pi. And then we evaluate this between 0 and pound 4, of which it's going to give us negative pi over 4r into e to the minus r squared minus 1. Okay, now the main thing with this is that this thing is going to go to 0 as r goes to infinity. Okay, so we are going to now summarize this. So we have got integral of e to the iz squared along C1 plus integral along C2 e to the iz squared dz plus integral along C3 e to the iz squared dz. According to Cauchy's theorem, this is going to be equal to 0. Along C1, z is just equal to z is just going to be equal to x. So that's just going to be I e to the ix squared. So this is going to be integral from 0 to r e to the ix squared dx. Okay, and then we have got the one along C2, which we just worked out a while ago. Maybe let me write it out. So along C2, it's actually going to be this one. Well, it's an upper bound. Yeah. Let me just write it out generically like this: e to the iz squared. We'll talk about it just now. And then along C3 is the first one we worked out. So it's yeah, okay baby, I think let's do this here. Okay, so this statement is fine. So, and it's going to remain. So what we're going to do here is we're going to take the limit as r goes to infinity. So basically we are deforming this this contour and making it bigger and bigger and bigger and bigger. And according to the theory of analytic functions, this result should still hold because this function is analytic. So when we do that, this first one is going to work out to integral from 0 to r e to the ix squared dx. The second one, so along C2, is this one here. We've already shown that that one goes to 0 because if this integral, which is bigger than this one, goes to 0, then that means our integral, and hence the integral we started with here, will also go to 0. And then the last integral we showed that as r goes to infinity, this one goes to negative square root pi over 2 e to the I pi over 4. So this is equal to 0. So this is infinity here. So this thing is telling us that therefore the integral from 0 to infinity of e to the ix squared dx, this is equal to square root pi over 2 e to the I pi over 4. Okay, so we are now going to go back to our expression here, and we are going to plug that one in here. Okay, so finally we are going to have, so therefore the integral from minus infinity to infinity e to the I lambda x squared dx is going to be 2 over square root lambda, and that integral is given by square root pi over 2 e to the I pi over 4. And then so this simplifies to square root pi over lambda e to the I pi over 4. So that result is has been derived. So you on the other hand, you are going to derive the related result. So just a small modification here: negative I lambda x squared dx. So show that this one gives us pi over square root pi over lambda e to the negative I pi over 4. So you're going to have to start with a or construct a relevant contour for your derivation. All right.